We have a great session with Imagimob. My name is Mary Benyon, and I'm a manager in the AI ecosystem team at ARM, and I'll be your moderator today. So first up, thank you again for attending. And if you would like to tweet to us and find all of our other resources, here's some links here that you can use. The developer YouTube channel is where we'll be posting this session once we're done. And don't forget to fill out the survey at the end. We're coming up on a year anniversary of doing these talks, and we've really had a great time with these, and we want to keep bringing you relevant information and content that you want to hear from us. So we are very open to suggestions, so fill out the survey. And if you do, we have presents for people who take the time to fill out our survey. So we will put you in a drawing to win an Arduino Nano 33 BLE board. Next up is just a peek at some of the upcoming talks that we'll be having through July. So these are all open for registration now. You can take a look at the abstracts. These are all going to be really, really good as well. I'm kind of biased. I think they're all great, but there's so many different topics. So check these out. And let's get to it. So today we have Imagimob. We've got Johan Malm, who is super smart PhD, master's in science, physics, specializing in machine learning, signal processing, numerical methods, and visualization. Johan, how are you doing?
Fine. Thank you for the introduction. Yeah.
Yes, of course. And just a couple things before I hand over to you, Johan. So please, as we go through the presentation, put your questions in the Q&A box. We'll be answering all sorts of questions at the end. So don't hesitate to put your questions, and we'll try to get to as many as we can. This is like a double giveaway day because Imagimob also has some hardware that they would love to give to some lucky attendees. They've got 30 nanos that they will be handing out. So we'll be pasting an email towards the end of the presentation that you can use to send in and get your chances of winning a board. So you have 2 chances today. So odds could be pretty high in your favor. All right, Johan, so I will hand it over to you. And you're coming in from Sweden today. So appreciate it's a little later in the day for you, but yeah, let's get started.
Exactly. So I'll be broadcasting here from my living room. It's very cozy and nice, but it's great to see that there are so many out there listening. Yeah, so thanks, Mary. I'll start from here.
All right. Enjoy, everybody.
So yeah, I'm Johan Malm. At Imagimob, I'm working in the research and development and customer projects, and also in our product team, where we build a really good development tool for Edge AI, because that's what Imagimob does. And I'll get back to that in a moment. So short about Imagimob, we were founded in 2013 with the idea that Edge AI, or tinyML, as we also call it, is going to become a big thing. And by Edge AI, we mean machine learning models that run on embedded hardware, like ARM microcontrollers. We started right away to build applications and proof of concepts in customer projects. But in the last couple of years, we have transitioned to become a SaaS company, where we actually offer our own development tools to customers, as well as our expertise in Edge AI. We are based in Stockholm, in Sweden, and we are about 15 employees. So, after a short intro, where I will share our vision and the essence of the tool that we develop, I will discuss the latest developments we have been doing in the audio space. In the last section, I will dive into some of our optimizations that we use in our embedded code. So our vision is quite simple. After having worked for many years in many embedded AI projects, we know that building a really good edge AI model requires a lot of expertise, and it is very time consuming. Writing code for embedded hardware is error prone. We want to simplify this process, and we have developed a tool that takes the user through the entire process, from data collection, data annotation, model building, evaluation, and finally generation of C code. And why C code? There are other frameworks out there that don't require translation to such a low-level language as C. But if we think about it, the first computers, they were created around 8 years ago, and there has always been a trend towards smaller and smaller hardware platforms. Compare your first PC and your current mobile phone, and you'll get the idea. We strongly believe that this trend will continue. And the interesting thing about this is that as we continue to push this limit, and we are always, so to speak, at the tiny side of this compute spectrum, the smallest platforms that will be produced tomorrow and in many years from now on will actually resemble the smallest platforms that we had yesterday and that we have today. So the bottom line is the major language for embedded software on these smallest platforms is, and it will continue to be, C. Anything more high level is quite unlikely. So that's why we focus on C code. And I will come back to more benefits using C code. Our development studio for embedded AI is a general tool, and we have worked with a broad set of different data streams like PIR, temperature, voltage, etc. And we have connected around 10 different sensor types into Imagimob AI. But we have also deepened the set of features and knowledge in certain verticals, like human activity recognition and radar, for instance. And using the smallest radar sensor in the world, manufactured by Acroneer, also here in Sweden, and you see this sensor here on the finger. We have worked closely together with Acroneer and another company called Flexworks to build the world's first gesture-controlled in-ear headphones that you see on this cartoon here. So the software for that product was developed entirely using Imagimob AI, and it was running on an ARM M4 MCU. Now recently we have extended the tool for developing audio applications, and I will use an audio project to walk you through the steps of generating an AI model in pure C code, which is our end result. And here you also see an image from the studio. But let's jump right into it. And this is how Imagimob Studio looks like when you start it up. So this is a clean project. So on this surface is where you do all your projects. And one of the key parts when constructing a successful AI model is to have your data in place. So since what I will discuss here is classification, this means having representative samples of your data and well-defined labels. The Imagimob Development Studio helps you with this part by using a graphical user interface. So here we have a keyword spotting project where we want to teach the model to distinguish between the words up and down.
Down, 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 down.
So this was obviously down, and we can easily click on the data files, inspect the data, and adjust the annotation of data samples or add new labels. And this graphical user interface is really handy when labeling your data and fine-tuning the labels. We have found that in over and over again in many projects. Okay, so when you're happy with the data, the next step is to add the data to a project. So first you create a new project like this. Then you add the data that we trimmed and fixed. When the data is imported to the project, you can see it up here on the top in the segments tab. The data is automatically shuffled into either the training, validation, or test data set, but this can be changed by clicking that little drop-down menu. The project workflow is now to work yourself downwards through the tabs. So here you set the amount of data in various data sets, and on the symbols tab, you can see how the symbols are mapped and how much of each class you have. So here we have two classes, it's up, and it's down. And also the implicit class that we call it the background, or like everything else, that's class 0. Right, so pre-processing the data in a proper way before inputting it to the actual machine learning model is really important to get a small and effective model. And on one hand, we are doing deep learning since we are not really doing feature extraction. But on the other hand, we are making the data easier to digest for the AI model, which in the end helps to reduce the size of the model. So we're somewhere in between, and it feels like that's almost like our own little secret, that we treat the pre-processing like in a very delicate way. And therefore we have also chosen to include a preprocessor in the studio, and we treat the preprocessor operations as layers in the same way as we do for the layers in the next coming neural network, like the classification part. You'll probably find this really nice since you don't need to add your own preprocessor in the final embedded code. So that's a real pro. And we have a library of operations to choose from. You can create different types of preprocessors and compare them visually. So here, for instance, we have a spectrogram of the audio data that we have defined like this, and we can look at it visually. So you see it's very similar, the different down instance here, and we can compare it to an MFCC preprocessor defined here. MFCC is usually used in audio processing. Produces compact and good features, smaller in size compared to the spectrogram data. So after having defined your preprocessor, it is time to generate the actual AI model. And for this, we use neural networks. We have an AutoML approach where the user can select a number of model architectures and model parameters. And from this, the studio will generate a set of architectures suitable for the data. So here we were choosing 4 model structures. And by model structures, I mean the number of different layers and and the types of layers, and 4 different set of learning rates and weight decays, so model parameters. And this will generate 4 times 4 equals 16 different models. And then as we can select one of them and look at this model and the different layers, and they are like randomly chosen in a certain space like this. When we now press start new training job, all these models will be sent to our cloud service for training. And then usually what you do, or what I do when I do a project like this, I run it overnight, and I'll look at the results the day after. And that's here. So now it's the day after, and the training has finished. So you can now look at the model statistics to determine which model you would like to use. And that model you can now download to your local computer. You can also download the model evaluation. This is really handy because here you can see on the timeline how the model performs in real life. And this is something we have found extremely useful in our own projects. So you can see here how the model would label the data and compare that to how the human would label the data on the bottom here. So the lower row is from the human, and the upper is from the model. And you can zoom in and go back and forth. And this is, as I said, very, very good like a complement to the more normal confusion matrices and so on, which doesn't tell you the whole story. Okay, now we're almost done with this project. The model is trained and evaluated, and we would now like to translate it to C code that can be compiled for your specific hardware. And what you do now is you click the final edge tab here at the bottom, and then you click build edge. And here you see a summary of the generated model, how large it is in terms of RAM and flash. And in the edge directory here, you get the actual C code, and you have the header file here as well. And this contains the preprocessor and the neural network. Okay, so now we have an overview of the platform and what it can do. I will now talk about the optimizations we have been implemented and are planning to implement. So what we just did in the last step inside the studio was to generate C code from a model and a preprocessor. And as I said earlier, the choice for translating machine learning models to C has many benefits, and for us it has been the obvious path already from the start. And one of these benefits is flexibility. So with full insight, developers can tweak the code for their specific needs. Portability. So virtually any platform supports and will support C in the future. And speed. C code can easily be modified to take advantage of specific hardware instructions, like ARM SimSys DSP or ARM SimSys NN, which I will talk about in a few minutes. There is no need for any runtime library or anything like that. The code can be statically compiled. But as I mentioned earlier, writing C code for embedded platforms is slow and error prone. and we have developed this C code generation tool that sits inside Imagimob Studio, and we call that Imaginet, this tool. And just to give you an idea how this C code generation works, the first step is to generate the TensorFlow model or other arbitrary Python layers that you can define yourself, either inside the studio or you read in an external .h file that you have been training in some other framework or tool. So here at the left, we see the preprocessor layers that you saw before. And on the right here, it's the actual neural network model. And inside our tool, we have mirrored all the Python layers to C code, and they produce exactly the same output given the same input. So we have that implemented as efficient C code. We call them ImUnits. And from these defined preprocessors and models, we generate a compute graph. And then we go over this graph and optimize it. So for instance, as starters, we don't use any mallocs because that involves system calls, but instead we use static memory allocation. So actually we have our own memory management. So at compile time, we allocate a chunk of memory. And since we know which buffers that need memory simultaneously, we can reuse this memory in clever ways. Another thing we do is matrices are transposed to ensure that we use memory in efficient ways. So we traverse element always row-wise. Constants are evaluated at compile time, and expressions are simplified, and loops are optimized. So these are all like general C optimizations that we do, but since we only do it like, yeah, we generate C code, so we don't, in every project we don't need to do this again and again. So we do this really good in this C code generation tool. And then from this compute graph, we generate C code. And here you can see a code snippet with the function calls in the compute graph stacked, very simple and very clean. I can just mention a few figures that are taken from a real project. And this is the in-ear headphone project that I discussed earlier. And the C code generated for this particular model had, it would fit in 12 kilobytes of RAM and 98 kilobytes of flash. And we used an ARM M4 to do all the processing and classification inside this little in-ear prototype. So this kind of C code is optimal when you want to deploy on the smallest MCUs on the market. And we have mostly in our projects used ARM M3 and M4 due to their performance and price. In some cases also customers have been asking for ARM M0. So we have been deploying on that too. Okay, so except for these more general type of C optimizations, we are just in the process of finalizing support for post-training quantization. And in particular, we are adding quantization support for LSTM layers. And quantization, or integer approximation, you can also call it, in signal processing is nothing new. But in machine learning and neural networks, this is something relatively new, and support for all layers cannot yet be found in all common frameworks. The basic idea for post-training quantization is to replace floating point operations with integer operations in the already trained model. So this is only used in the inference part, and we are not training the model using integers. So what we do is that we go over all the tensors in our workflow, and we note down the min and the max floating point values. Like in this case, it would be 5 and -2. The max and the min for this particular tensor or buffer. Then we divide the range into the number of buckets available for that integer type, which would be for integer 8, 255 buckets. And by using the bits in that way, we can get the most out of every bit, so to speak. And then we can use that to define a linear mapping between integer and floating point values like this. So we can go from int to float and vice versa, with some loss of accuracy, of course. And also, by doing some more arithmetics, we can quantize all the operations in that compute graph that you saw earlier, so that it can look like this in a schematic way. So each operation will have its own quantized version. And the benefit with all this is that, like on ARM M0, where you don't have any floating point unit, doing floating point operations is very much penalized in terms of CPU usage. So it's an important optimization to do for the smallest MCUs. And in general, models will get up to 4 times smaller and 3 times faster, even if you have an FPU available. So the next optimization we have in our roadmap, so it's something we definitely want to do, but we haven't had the time for it yet, is to replace certain function calls with hardware optimized versions. And a timing example that we did, again on this in-air model that I showed earlier, shows that this can be extremely beneficial. For example, for this application, 65% of the compute time was used in convolution 1D in that layer, where close to 100% of all operations are dot products. And this can be optimized using multiply accumulate operations or MAC operations. For the rest in this model, we had mostly dense layers where optimized multiply add operations can be used. In other words, a very large portion of the instructions can be optimized, like probably more than 90%. And since virtually all models run on ARM processors in the end, a natural start for us is to implement support for SimSys NN and SimSys DSP. And the C++ API is easily integrated into our C code, because here we have the call to the convolutional layer. So it's just to replace those that code with the C++ code instead. So that's actually it for me. Let's see if you have any interesting questions.
That is not it for you, Johan. We have so many questions.
All right.
Yes, you are
Great.
far from being over. Thank you, everybody, for all these questions. So Johan, let's just go through these. I'll just start at the top here. So Jalal is asking, how accessible are your tools for people who are not very skilled in C++?
Very accessible. I mean, that's the whole idea, to democratize this and make it available for all engineers and all other people that really want to build machine learning models. And we want people to focus on their skills and their applications instead of being experts in C++, C, and all the difficult parts that has to do with embedded programming.
So would you expect just sort of a baseline understanding of C++ in order to be able to successfully use the tool?
So when you develop when you follow this workflow that I showed you, you have nothing of C or C++ there, but then as soon as you click build edge, you'll actually get the code, so it will be produced for you, and what you need to do in the end is to have a main function that calls basically two functions. Like, you initialize the code and you call the compute function, and that's it. So you take your sensor data and you just shuffle it into these functions, and that's it.
There you go. Nice. Okay, next. So Carlos says he's working on a Jaguar conservation project using edge computing and AI. The couple questions is, does the software run on Linux? And have you tested the code by chance on Sony FreeSense or Arduino Portenda? And can it run on any core? So it's actually 3 questions.
So
we'll just take the Linux question first, I guess.
Yeah. So if you have a C compiler, the answer is yes. It's that, and that's our, as I said, the main. We want to make this. We don't want to tie it to a certain platform or anything like that. It's pure ANSI C code that you can run on any platform that has a C compiler.
Cool. And did you happen to test it on the C Sprints or the Portenda by chance?
Ooh, no. I mean,
Okay.
as I said, 90+% of the projects were ARM.
Yeah.
A few others, but there are very few.
Yeah. So Carlos, you have to grab the tool and make a model and then test it.
Yeah,
so
would be
sounds
nice
like it should work.
Nice to hear how it goes.
Yes. I guess we can put an email address in the chat. So actually, if anybody who is attending this wants to get in touch and has questions, you can reach them via an email address that we'll put in the chat. And this actually might be a good time to remind people that Imagimob are giving away some Arduino BLE boards. So Tobias, whenever you get a moment in the next few minutes, if you want to put that email address in the link, and that's the one you guys can use to try to win one of these pieces of hardware. All right, moving on to the next question. So Chandra's asking, does your tool support the choice of using int8 or int32 instead of float in case the target MCU does not have the support of floating point processor?
Right. So that's our idea, that you can with this in place that we are just finishing up right now, you can use this both on the platforms that have an FPU. Also there you will see a lot of gains, but also, you know, on the platforms that don't have an FPU, it will be like lightning difference. So you could expect 3 to 4 times speed up on the platforms, even if you have an FPU. I would guess.
Great. Okay. Let's see. Is it possible to train on the embedded device?
No, we don't do that at the moment.
Okay.
Actually, but yeah. So, and we use really powerful machines to do the training. We've seen that has worked very well.
Yep.
In all projects so far.
Yep. Does your tool support the choice of frameworks, so TensorFlow, PyTorch, for your model generation?
Yeah,
I guess
that's a good question. We've been talking about that a lot, which framework works to support, and we are going to support more. Right now, it's only TensorFlow, but I mean, there are so many people using that, so it has been enough so far, but we know that many use also PyTorch, for instance, so I think we will add that shortly.
Great. How are you handling the loss due to quantization of the weights?
The loss, you mean like the error you get?
Yeah, or yeah, there's no elaboration, but when you do quantization, you lose sometimes accuracy or performance.
Yeah, I mean, that's unavoidable to do that.
Right.
And actually, what we do is, I mean, you can do a lot of clever things there. And for instance, when you choose, I mean, we go over the whole compute graph and we look at the min and max values, as I said, and if it's like a very important operation that has maybe a very big range, you can go over to int 16 only there, and then you switch back to int 8. So we try to be focused on int 8, but we can momentarily switch over to int 16 or even int 32. And I mean, if you do int 32 all over the place, you have 4 billion buckets. So then you should, if precision is what you're after, we could do that. So, and then you can, yeah, so it's like a balance act between CPU and memory.
Yeah, it's like a recipe. It's like a souffle. You don't want it to like collapse on you.
Yeah.
Let's see. Here's a question. Could you explain a little bit more on how the automation of expression simplification happens when you try to convert the model to C code?
Right. So that's something we do more in a manual way, I would say, because we know how certain expressions will look like in the end. So then we just write it out more explicitly like that.
Okay.
So yeah, it's not a symbolic calculator or something like that.
Here's a quick question from Felix. Hello, Felix. Is the quantization spec, the int8, a custom Imagimob one There's a mention of support for SimSysNM, so that indicates quantization follows TensorFlow Lite Micro into 8 spec.
Yeah, when we started with this quantization thing, we used TensorFlow Lite to get this these quantization parameters like the 0 point and the scale values, because they have handy functions to where you input your data and it will find the quantization parameters for you. But then when we went over to LSTM, that support was lacking, so we implemented those functions ourselves now for yeah.
Okay, still lots of questions coming in. Thanks, everybody. We'll try to get through as many as possible, maybe run another 10 minutes or so with questions. So that should give us, I think, enough time to get through all of these. Let's see. Quick question from AJ. Any plans to generate VHDL for FPGAs?
That's an interesting one. We have been talking about, I mean, we have like we have the studio where you like develop your models, and we want that to be really easy to use, and we get a lot of nice feedback on that building your models is now much easier. But then like we have this Imagimob edge part where you convert to the edge, and we want that as well to be like the best in the world. So we have those two things to focus on, and we share the resources as well as we can between those two. And definitely we would like to optimize more, and so that's something really interesting. But I think the next step is like this SimSys and see where that takes us. So we take it a little bit step by step.
Yeah, great. Let's see, here's one from Chandra. The difficult part of porting models to MCU is fine-tuning the memory requirements of our models. So for example, when we use TensorFlow Lite, finding the optimum tensor arena size for a given model. Does your tool provide any mechanism or support for that? I guess
support for what? To
fine-tuning memory, and does your tool allow, I guess, people to turn knobs and sort of experiment and fine-tune the memory requirements?
Not so much at the moment. So we have this button, basically a button where you convert to C code, and bang, you have your C code.
Okay.
So and that will probably do a better job than it depends, of course, how skilled you are, but we have put down a lot of development time doing that as slim as possible.
As possible, yeah.
But of course, so right now we have usually quite little RAM usage because we use the RAM memory for buffers and things like that, variables. But the weights we put in flash usually, like constants, and one could think of options where you select different types of memory areas to put these things if you have more of one or the other. But currently, no.
Okay. There's a couple questions that are kind of all around the same topic around just access to the tool. So how do you download the tool? Are there eval or trial versions of Studio available? And is there a resource with examples of your past projects that could be browsed? Angelo would like to start a project to predict industrial machine status using vibration and acoustic data. So I guess how do people get the tool? What's the deal with eval or trial versions? And, how do people get, start using this?
Right. So if you go to our web page, you find everything you need to sign up on a free trial. That's usually the first step. Then you can try the tool for free, and when you start the free trial, we have a like a session together with you, and you normally the potential customer sends us some sample data so that we can really fine-tune this session towards their own data. But we also have tutorials on that you can download, for instance, accelerometer data that we have prepared, and you can test run a project like that. But the first step is free trial, and then
I've posted the link, everybody, in the chat, and actually I'm just looking at it. If you go to that link, there's a button that says sign up for Imagimob AI free trial. So please go there, and that's how you can get started. Let's see, let's grab a few more questions here. What is the maximum number of words you used on training for keyword spotting, and how many approximate samples of each word?
The first question was how many?
Maximum number of words you've used on training for the keyword spotting, and how many samples for each word, I guess, was required for the training.
I think we use somewhere around 5,000 to 6,000 words. It wasn't that big. I thought actually that we would need more data, but what we actually did instead, when like the first attempt was not so good, so I thought, okay, let's add more data. But actually, when we went in using this graphical tool, we went in to look at the data. We actually, in the first step, we trained using one word at a time, but that wasn't so great. So we actually put together 20 words in one file, so that you also got, when you slide your window over the data, you will not only get exactly the word, you will also get half a word, or like 1/4 of a word, things like that, like all these possible samples that you would get when you run the model live. So we did that. We took away some outliers, like strange low amplitude words, strange words, things like that, that you normally think that, okay, let's add as much junk as possible, but no, we removed that. And then we had like real good quality data, and that made it the model much better. Even, I mean, then I tested the model on myself, and I wasn't in the database. I have even a very strange Swedish accent, but it worked very, very well on
right. Yeah, nice.
We've actually seen the same in this in-air project, that reducing the data set, having real like high quality data helped us a lot.
That makes sense. Let's see, to integrate IM AI generated C code into my embedded system, do I need some additional library support like tinyML pre-built and integrated in my ARM system?
Yeah, no, you need to, as I said before, create the main function where you call our compute function, and then compile it for your ARM hardware.
Okay, easy.
Yeah.
Let's see. Would Imagimob also serve as a platform to share pre-built models and contribute in the creation of data sets? What are the sensors that Imagimob would provide support for?
Oh, that's a good question. So when I talked about these specialized verticals, that's exactly what we do there. So we actually provide like already labeled data sets, and we call it content packs. And we have that now for the radar, but we will also do it for the audio vertical.
Great. Here's another one. In your tool, you showed pre-processing before training. Could we add custom digital signal pre-processing C code that would be running on the device to your tool?
Yeah, exactly. So that's the great thing. You can put in your own units, like we call it, and if you have then the same the code in Python and in C that does the same thing, you can build. You can yeah. So it's very flexible. So there you can put in perhaps some very optimized FFT or other common preprocessors that are used in signal processing. So so as I said, our idea is to chew the data like a little bit, and then you give it in some sense raw format to the model. That has worked very well for us. We did feature extraction in the past. Then we moved over to like putting the data in a real raw format, like directly from the sensor. But that made the model really big, and it doesn't really make sense if the data is really like sinusoidal. The FFT of it is what you would give the model. Then it can digest the data much better.
Great. Let's see. Here's a quick one. Does the tool support quantization aware training as well?
No, we haven't needed that so far. I think we will get very far with the post-training quantization. But we'll see.
Okay. All right. I think we're almost out of time. Let me just see if we can get one more question in here. Kind of broad. Can you please explain your different labeling strategies?
Oh yeah, that's a very good question. It was almost like we were almost not aware about it ourselves until we found out that it's extremely important. Because what we mean by that is okay, we put the label on the timeline, so we think that the label is well defined, but actually when you think about it, when you traverse the data with a fixed window, you have to decide at some point when is that window going to be labeled as nothing, like the background noise, or the word down. So at which point are you going to switch over to either of the classes? And that's what we mean by this label strategy. So we try to define this Y vector that is used for in the back propagation and the training. And we have different strategies. So one is most frequent, where you take, it's like a voting strategy. So you take, if you're mostly inside the class, you say that okay, now you're in down. But we also have other approaches. So one drawback with the most frequent label strategy is that if you have a very big window and a very tiny event, it can almost go extinct by this voting strategy. So if you have a big window and you have a, like the other class on the sides, it can vote and say, no, this is like the background class. So we developed this midpoint strategy, and I have too little time to describe that one here, but it's it's definitely
that's for another time. We could probably do a whole prezo just on that deep dive. So if people are people are into that, we're happy to bring that to you.
Yeah, we have many of these things that we have like discovered in all our projects, and we have like put them into this tool.
Cool. That is awesome. Well, I think we're pretty much out of time. I'm sure people have to run and go to their next meeting or, get on with their day. So thank you so much, Johan, and thanks everybody for attending. If you want to flip to the next slide real quick, Johan, I just want to wrap things up again with everybody. So here again, here's where you can find us on Twitter, our YouTube channel, and our next upcoming virtual tech talks. Please don't forget to fill out the survey. I look at these things and I want to see all the nice things you say about it, but also I'm more curious about what we haven't brought to you, things that are missing, things you would love for us to do for these tech talks, and we'll try to accommodate that. And then lastly, before you all run away, Dev Summit ARM is our flagship conference that is coming up in October. You can go to devsummit.arm.com for more info. Currently, there is a call for papers open. So if you would like to submit and do a tech talk, there's all the instructions there, and please feel free to contribute. And also, once registration is open, make sure you register and attend. It's going to be a great event this year. So thank you very much for everybody. And thank you, Johan, so much for this fantastic presentation. It was great. Really good, great questions, everybody. I love when we have an engaged audience. Yeah. Please go to imagimob.com for any other further questions or inquiries. They're happy to help you out. They'll respond to your inquiries. And don't forget to email the other email address for a board, a nano BLE from Imagimob. Thanks, everybody. Enjoy the rest of your day. Bye.
Bye. Thank you.